And we're back. It's Major Cunningham again with the Astro Department. Wanted to walk you through some examples, pretty good examples from last year. At least this was last year's homework for ground tracks. I want to walk you through kind of the basic things that you might encounter with these kinds of problems. So let's just think through this. So essentially, a ground track is the shape that a satellite traces out on a map of the Earth. And what we do here is, in Astro, we ask you to either one of two situations. Situation one, we give you COEs. We want you to draw the orbit. Situation two is just the reverse. Given orbit on a map, find COEs. Okay, so my first example problem here is an example of a situation one, if you want to call it that. I'm given 6 COEs. Actually, we'll get into that. There's 7 here. A rare thing, but basically this is another very recipe-driven process, and we're going to start at A, march our way down. First thing we want to do is we want to find our delta n. Now remember, what is delta n? Well, let me rewrite my sun-major axis here. Delta n is a portion of the orbit. How's the best way to do it? Like if my finger were delta n, that would mean that 40 degrees worth of this orbit is not covered by the orbit. 40 degrees worth of the Earth, sorry. 40 degrees worth of the Earth are not seen by the orbit. So basically delta n on our map shows us how far right we can draw our sine curve. So with that in mind, let's use A to find our period. Straight off the equation sheet right here, we're going to use the old 2 pi a cubed over mu to give us what our period is in seconds. And this is important. Remember, seconds is what we want out of this. Mash some calculations here. Okie dokie. Excuse me. Okay, so that gives us almost exactly 14,400 seconds. Let's convert that from seconds to hours. So we'll divide by 3,600 to accomplish that, because there are 3,600 seconds in an hour. And that gives us almost exactly on the money 4 hours. Excuse me. So that's great, because now finally we can use the equation on the bottom left of the equation sheet. The only equation for ground tracks is very simple. P equals delta n over 15 degrees per hour. Oop. We can solve that for our delta n. So that gives us, if I'm not mistaken, 4 hours times 15 degrees per hour, 60 degrees. Okay, so that means my delta n is 60 degrees. So that means, if you can see these very small blocks on the bottom here, each is 20 degrees, right? So if you, for example, start at 0, goes 0 to 20, 20 to 40, 40 to 60. Okay, starting from the rightmost side of the map, giving myself 60 degrees worth of delta n, here's how this works. There's 20 degrees worth, there's 20 degrees worth, there's 20 degrees worth. My delta n, 60 degrees. Okay, what that means is my sine wave cannot come any further than, how do I put, like this right here, right? This is where the delta n ends. Okay, great. All right, next thing's next. Eccentricity of 0. all this tells us for the drawing is we get to draw a symmetrical shape. Symmetrical sine wave. As opposed to if eccentricity is between 0 and 1, which is really hard to draw. It's much easier for us to give you eccentricity of 0 when you're going from COEs to drawing, because then you don't have to try and deal with free-handing an oddly shaped orbit. So I suspect that it's more common on these homeworks and to see an eccentricity of 0, because otherwise it's tough, even for an instructor, to freehand an orbit like that. So great. So when it comes time, I get to draw a symmetrical sine wave. Check. Inclination of 50. Well, what does that tell us? Well, that tells us how high and low our sine curve is going to be. What does it mean in real life? Well, you guys know inclination is the highest latitude and lowest latitude, right? The satellite actually sees. So in this case, a little hard to see there on the edge, but between 40 and 60 is 50. So I draw a line across there, and I'll draw another line down here at negative 50 degrees. Okay, now I have my up-down bounds and my left-right bounds without trying to oversimplify. Ran is 0 degrees. How nice. So I'm going to start drawing my orbit over here on the left side of the page. Unrelated to Ran. That's just kind of a nice thing to know. Little omega is undefined and true anomaly is undefined. Well, that's odd. Why would that be? Well, because we have a perfectly circular orbit. And there is no perigee with a circular orbit, because every area of the circle is equally close as every other area of the circle to the Earth. So we're going to use this thing we call argument of latitude, U, and that's 90 degrees. So before I go any further, I'm going to try and draw my sine wave. And here's how I do this. I keep calling it a sine wave. That's not completely correct. I'm going to draw my shape. How about that? My orbital shape. So let's see. How many blocks are between left side of the map and my delta n bounds? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that means the midpoint should be at 7.5. So 1 block, 2 block, 3, 4, 5, 6, 7, and then another half block. So that's just going to be the midpoint of my orbit. All right. So I'll start at the left, draw my way up. Oh boy. See, this is where it gets challenging. It becomes an arts and crafts project. Okay. Well, I'm not sure I counted that off right. 8, 9, 10, 11, 12. Oh, 1, 2, 3. Yeah, that's correct. Just looks weird. Okay. Anyway. Draw my orbit back down there. My intent, what I was trying to do, was have the top of the orbit touch this dotted inclination line, and same with the bottom. As you can see, it can be a challenge to do. So starting here at the ascending node, I think you guys would, if my orbital motion is like this, you might buy that, the satellite was down here and hit the equator, so now it just passed the ascending node in my little drawing here. And then it says the satellite's current position is argument of latitude of 90 degrees. So starting at the ascending node, tracing out about a quarter of the orbit. Places our satellite right here. I always draw little solar panels on my little box, so it's evident that I know where the satellite is. So there you go. So we annotated delta n, and we put an X at the satellite's current location. It's right here. Are we going to ding you for not being on the exact hash mark between two? No, there's just no way. You can't eyeball that. You're only human. And so are we. Cool. So number 1, done. Let's tackle another example. Let's go the other way. Let's go situation 2. Remember, situation 2 is where we're given a nicely drawn out orbit and then asked to find some COEs. So here's our nicely drawn orbit. Let's try and find some COEs. Okay, and just as before, we're going to start with some major axis and work our way all the way down. Pretty straightforward. Okay, semi-major axis. Well, what do I know? Last time I was given semi-major axis and I used the period equation to get delta n. Well, now I'm just going to eyeball delta n off the map. There's a delta n, and that's how many blocks? 1, 2, 3, 4. 4 of the 20-degree blocks, 80 degrees. Now, that's not my only delta n. This is tricksy. This is tricksy here. There's some delta n over here, too. And I see 1, 2, 3 of those blocks. So my total delta n is that 60 degrees on the left plus the 80 degrees on the right, and that gives me 140 degrees total of delta n. Excuse me. So now we're going to use this good old-fashioned equation to go back the other way. 140 degrees over 15 degrees per hour. Let's see what that comes out to. About 9 hours, 20 minutes. Right on. We need to convert this from hours to seconds so we can use it in the period equation. And that gives us 33,600 seconds. We'll plug that into our period equation here. Oops, I made that too big. Oop. Man. Excuse me. I'm going to solve algebraically for A. Oop. Notice how I am plugging this in, period in seconds. I cannot emphasize that enough. Oops, forgot my 2 squared. It's basically 4 pi squared on the bottom because 2 squared. So, okay. All raised to the 1/3. I'm running out of space. No pun intended. Although it is a good pun. Okay, some ridiculously huge number, but not to worry because we'll raise that to a tiny power, and that'll give us something nominally sane. So I got 22,505 kilometers, 0.34. Okay, so that is my semi-major axis. Cool. Remember units. Okay. Check. Now for eccentricity. Okay, from a map that we give you for the purposes of Astro 310, you can't really tell more than, is this sucker symmetrical or is it not? If it's symmetrical, eccentricity is going to be 0. If it is not symmetrical about this axis right here, then it's between 0 and 1, right? It's an elliptical orbit of some kind. Don't be tricked. Count off the number of blocks. Now, this one is clearly not symmetrical. This is a little tiny part of the orbit. This seems like a huge part, or a lot of ground's being covered anyway. Yeah, not much ground covered here. Only 1, 2, 3, 4 blocks. And then this part covers 1, 2, 3, 4, 5, 6, 7 blocks. Clearly 7 bigger than 4. But what if I were to give you, 7 blocks here and 8 blocks here? Your eye might be tempted to think it's symmetrical. Count the blocks. Don't be fooled. Get the points. That's our mission here. So, as I said, 1, 2, 3, 4, 5, 6, 7 blocks being covered up here. Only 4 here. So all we really know is that eccentricity is somewhere between 0 and 1. And one of my students pointed out to me, well, sir, you could back out more information than just that. And that's true, but for Astro 310, we're not asking you to do that. So not to worry. Okay, inclination. How high does this orbit go? It goes 40 degrees north and it comes down to 40 degrees south. So my inclination, 40. RAN, when I'm going from picture to COEs, I can't really detect where my RAN is because here's an ascending node. Here's another ascending node. I don't quite have enough to say anything more than RAN is unknown. Do not write undefined. Okay, don't write undefined because it probably is defined. RAN probably has a value. You just can't tell it from the map. I can't tell it from just the map. Okay, argument of perigee, though, we can. So let's look right here. That is the ascending node. Over here's another ascending node. Our satellite's direction of motion is like this, right? In one full orbit, the satellite covers way more ground. Look, it starts over here like at the same latitude as Vancouver, or longitude rather, and then screams across all the way towards the middle of Africa, and then it slows down and it just covers from like Africa over to India. And I say just as if that's a small distance. It's not small, but compared to how much ground it covers up here, it is quite small, right? This part of the orbit here pales in comparison to how much ground gets observed by the satellite up here. So we can say the satellite is moving way quicker up here, much more fastly. It's moving much quicker. So perigee is up here somewhere, and apogee's got to be down here somewhere. Okay, so we've established that. So perigee is up here somewhere. Now where? The satellite is covering the most ground. So how do I put this? Covering the most ground eastward at this location right here. How do I know that? Well, you still have some upward motion here all the way towards right here. Boom, then it goes completely vertical. So at this point, that is perigee. I label it for myself. It doesn't ask you to. I label it for myself. Okay. Argument of perigee is measured from the ascending node up to where perigee is. So this looks like about 90 degrees worth of the orbit. Right? It looks like about a quarter. There's a quarter, there's a quarter, there's another quarter, there's another quarter, right? 25%, 25%. That's as specific as you're getting. Do not use the blocks at the bottom for argument of perigee. Okay, don't use that. True anomaly is the same way. Don't use the blocks at the bottom. So to get true anomaly, we start measuring at perigee, right? So there's another quarter of the orbit. There's a quarter, and there's a quarter. It says X marks the spot for the current location. So from perigee, measured around the satellite's direction of motion to where the satellite is currently, I add up the quarters of orbits that I have, and I get that true anomaly is 270 degrees. And we have officially finished the problem and gotten the points. Ta-da! Cool. Okay, next and last. On this problem, it says, briefly explain why portions of this prograde ground track appear to travel westerly. Well, first of all, when it says prograde in all caps, what that means is the direction of motion is like this. But if that's true, it looks like it's screaming eastward, you know, coming from down here, continues up this way, and then slows way down, kind of tracks backward. Looks like it tracks backward. Does the satellite actually go backward? No. Well, it depends on where you're standing, I guess. But in the map, it looks like it travels backwards. It's not really true that it travels backwards. Again, let's look at how much ground we're covering. You guys would probably, I think, buy that from, I don't know, maybe right here-ish over to here-ish, covering a lot of ground, right? Lots of ground. So we are moving quickly. Okay, we're moving fast. V equals fast. Okay. But up here we start to look like we're turning around. What's actually happening is the Earth is rotating under the satellite's slow orbit motion faster than the satellite can actually cover ground. So that 15 degrees per hour that the Earth rotates eastward, the satellite is screaming so fast as it passes the ascending node. That 15 degrees per hour the Earth is rotating is not enough to stop the satellite from seeing a bunch of ground. But when it hits apogee, it actually starts to slow. I mean, it's very, very slow, right? Here we are approaching apogee. We get to apogee right here. Then we start to speed up a little bit. Point is, for this orbit, it's very weird, but perigee is right here. Apogee is right here. So my point to you is that when the satellite is approaching apogee and following apogee, the Earth's 15 degrees per hour is actually rotating under the satellite quicker than it can cover ground. So it looks like the satellite's tracking backwards, but it's not. Ta-da! And I would write that out. All right. Well, cool. Thanks. We'll see you next time.